It's a good thing your friends, now I am recording this, reminded me to record this because I forgot all about recording. So they're going to get a real fast, quick review. Geometric means are in the means position of a proportion. Geometric means are different than the average, the algebra mean. So the means position in a proportion, if I did the cross products, x times x is x squared equals AB, which means x, if I took the square root, is the square root of a times b, and that is the formula we can use to find the geometric mean, which we did right down here. Geometric mean between 5 and 45 is the square root of 5 times 45. This is like when I do these recordings when none of you are here and I'm talking to an empty classroom. When I do this one over here, geometric mean between 12 and 15. If we multiply 12 and 15, we get 180, which is not an integer if we take the square root. So we want to simplify that square root of 180. And I know everybody on basketball remembered their Algebra 1, and they remember how to simplify square roots. We look for perfect squares that go into 180. And 36 is the largest perfect square that goes into 180. 36 times 5 is 180. So I can separate it and do the square root of 36 and the square root of 5. And the square root of 36 is the number 6. So 6 square roots of 5 is the exact answer for that. This down here was if we didn't pick the largest perfect square. We picked a 9. Well, we have to go through several steps, but then you can still arrive at 6 square roots of 5. And the second thing we had is right triangles. Right triangles. When we draw an altitude from the right angle to the hypotenuse, it divides up that triangle into 3 similar triangles. And you will need to study the 3 similar triangles right here. They list out the 3 similar triangles. And here's an example in your book. You don't get quite as much time as the others got for 3 similar triangles that match up. All right, now we are all back together again, right over here. Right triangle, we are going to draw an altitude to the hypotenuse. We're going to call that length h, where we have divided up the 2 segments of the hypotenuse. We're going to call one x and one y. And across from the original angle A, that's where we get side A, etc. Across from B is side B. Across from C, that right angle is side C. Notice it way down here. And what we're going to do is split out these 3 similar triangles, the original one, and the little one, and the big one, and we are going to write down the proportions that are going to be true. So let's look at this first proportion they set up. If we have similar triangles, remember corresponding sides are proportional. So if we go to the shorter leg to the longer leg, remember in a right triangle, we have 2 legs and we have a hypotenuse. So the shorter leg is the one that's shorter. So the shorter leg to the longer leg is B over A. That's what they did in the first place. And then they're just going to follow that pattern of the other 2. Shorter to the longer leg is x over h. So that's what they wrote, x over h. And then over here, shorter leg to longer leg is h over y. H over y. And notice in this proportion, now there's a proportion that involves all 3 of the triangles. But in 2 of them, what position is this h in? The means position. And when you have the same value in the means position, that value is called a geometric mean. We'll use the word mean. It's called a geometric mean. H is the geometric mean between x and y. Now let's come to our original picture right up here. H is the geometric mean between x and y. That is going to lead to a theorem. The altitude is a geometric mean between the segments of the hypotenuse. That is this theorem right down here. Let's read the theorem, then we'll go back to our picture. The altitude drawn to the hypotenuse of a right triangle. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into 2 segments. We're calling them x and y for the moment. The length of this altitude, h, is the geometric mean between the lengths of these two segments. Right back up here, we just saw it. That length of the altitude is the geometric mean between x and y. That's the first geometric mean relationship in this picture. Now, they did another set of proportions right here. They took the hypotenuse to the short leg. So they go all the way back to the original, and they're just going to write out hypotenuse to the short leg. So if I go hypotenuse to the short leg, it's C over B. C over B. Hypotenuse to short leg, B over X. Hypotenuse to short leg, A over H. And if we look at the first two that we wrote, guess what we get again? We get a geometric mean. B is a geometric mean. Let's find it in our original. Where is B? B is a leg. And we discover that B is a geometric mean between C and X. Let's figure out what that is. C is the whole hypotenuse. And X is the segment of the hypotenuse that is adjacent to that leg. What does the word adjacent mean? Next to. Adjacent is next to. You are next to or adjacent to the person beside you. So what we see here is a leg of the original triangle is the geometric mean between the whole hypotenuse and the segment of the hypotenuse next to that leg. That's what this says. Now we're going to find this last one actually says exactly the same thing. Let me clear this off, and we will clear this off and do our last proportion down here. So we're working on this proportion, hypotenuse to longer leg, hypotenuse to longer leg, hypotenuse to longer leg, C over A, B over H, hypotenuse to longer leg, A over Y. They wrote them all out here. And the first and the last things we wrote have A in the geometric mean position between C and Y. Let's come back up here. A is a geometric mean between C and Y. Guess what? A leg of the original is a geometric mean between the whole hypotenuse and the segment of the hypotenuse that is adjacent to that leg. These last two things are the same statements. Those last two statements are this theorem. The hypotenuse of a right triangle separates that the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. We've called it X and Y. The lengths of the leg of a triangle, the length of a leg of a triangle, and that's the original, doesn't matter which leg I pick, we're going to pick A in this case, is the geometric mean between the length of the hypotenuse, the whole hypotenuse, C, and the segment of the hypotenuse adjacent to that leg. And there's the segment of the hypotenuse adjacent to the leg. A is a geometric mean. If A is a geometric mean, I will place it in the geometric means position. And it is a geometric mean between the whole hypotenuse C and the segment of the hypotenuse Y. They will go in the extreme positions. So now let's apply that right over here and see what we can do. Since X is the measure of the altitude, so right over here is X. Drawn to the hypotenuse of triangle JKL. So triangle JKL was the original right triangle. They drew the hypotenuse. X is the geometric mean between the segments of the hypotenuse, 20 and 5. X, if I'm going to figure out what X equals, I'm going to write a proportion, and I'm going to put X in the means position. And it's a mean between 5 and 20. Doesn't matter if I go 5 and 20 or 20 and 5, do you think?
No, it doesn't.
No, doesn't matter. And if I cross multiply this, X times X is my X squared. 5 times 20 is called 100. And then if I took the square root of that 100, what do you get for X? 10. X must be 10. And that came from the first theorem. We just have two theorems. Since Y is the measure of a leg, here is Y right over here. It's the measure of a leg of the original. That means it is a geometric mean between the whole hypotenuse and the segment of the hypotenuse next to that leg. Now that whole hypotenuse would be 25. So if I want to figure out what Y equals, I am going to put Y in the geometric means position. Now, the reason I use the proportion here instead of the formula is because later on, we sometimes have expressions like x plus 3 or something like that. And it's a little more confusing to have in the formula, and so I usually do it this way. So that leg's a geometric mean between 25 and 5. What's 25 times 5? 125. What is the square root of 125? Ah, that's not an integer. Where's the perfect square that goes into it? 25. How many times?
5 times.
5 times. You can think back to where we got it. Square root of 25 times the square root of 5. What's the square root of 25? 5 square roots of 5. That is the answer that makes us happy. And the last one down here, if I'm trying to figure out what z is, if we look back here at the original, I have a leg of the original. Z is a leg of the original. So it's a geometric mean between the whole hypotenuse, there's that 25 again, and the segment of the hypotenuse that's next to it, between 25 and 20. And so if I want to find z, again, I'm going to put it in the means position. It's between 25 and 20. What's 25 times 20? So if we go to take the square root of 500, do I get an integer? No. So what's the largest perfect square that goes into 500?
100.
100. How many times?
5 times.
5 times. So if I have the square root of 100 times the square root of 5, that's called 10 square roots of 5. There's our answer. All right? You guys ready? X. It is a leg of the original. Therefore, it is a geometric mean. Between what?
The whole side of the hypotenuse.
The whole hypotenuse, which is how much? 33 and 8. We need to pick the segment that is adjacent to that leg right over there. So we're going to take our cross products. What is 33 times 8?
264.
264. I bet that's not a perfect square. Perfect square that goes into 264. You may even want to write a list of perfect square numbers. I don't know if that helps you. 25? Does 25 go into these? Doesn't go into these.
Not even 9 does.
We only care about the perfect squares. Let me go back to my list over here.
4 goes into it.
4 does? Does 16?
Probably 16.
16? No? I'm hearing yes and no.
No, it doesn't.
No? Okay. Maybe it's 4. Now here's what we will be able to figure out is that really the best one? Well, I don't know. 4 times what is 264? 66. How I can tell is there a perfect square that goes into 66 evenly?
No.
There's not. We found the biggest one. What's the square root of 4?
2.
2. 2 square roots of 66. Now there's an approximate decimal that would go with that. Let me jump over to this one right over here. Let's say I am trying to solve for x. Is x in a geometric mean position in that picture? Is y in the geometric mean position?
X plus 9?
Let me review. There are 3 geometric mean positions.
Yeah.
The altitude is a geometric mean, right? And it's the geometric mean between these two things. A leg is a geometric mean. A leg is a geometric mean between the whole thing and the segment next to it. A leg, it's the same thing, is a geometric mean between the whole hypotenuse and the segment next to it. So let me come back to that x. Josh B, can you help me out?
We know the altitude, so we can put the altitude in the geometric mean position.
Exactly. The altitude is a geometric mean. I'm going to put it in the geometric mean position. 12 and 12. It is a geometric mean between what and what? X and 9. We can solve this. So the unknown doesn't have to be in the geometric mean position. Let's try this out. X times 9, or 9x, is going to equal 12 times 12, which is 144. So if you divide by 9, 16. 16. We just figured out what x was. Now we're going to see some more examples when we get to your book here. But notice, it doesn't matter whether it's a number or an unknown value in the geometric mean position. I can still set up a proportion using geometric means. Here's a cool application. Zach wants to order a banner that will hang over the side of his high school baseball stadium grandstand and reach the ground. To find this height, he uses a cardboard square. All you can use is a piece of paper or anything that's square, your book, to line up the top and bottom of the grandstand. He puts his book right over here, and he sights up that book, so he's looking at the top, and he sights down that book to see if he's looking at the bottom. That's what he's doing here. He's looking at the top, and he's looking at the bottom, so he moves until he's in the right position. And then he measures. Oh, 10.5 feet away here. He knows his eye happens to be 5.75. It's kind of bright or dark over there because it's bright over here, at least for me. I don't know if that helps you. 5.75 from his eye to the ground, and x from his eye up to the top of the stadium he doesn't know, but we're going to see if we can't figure out the height of that stadium. So look at this picture. There should be a geometric mean in this relationship. What is the geometric mean?
Altitude.
The altitude, the 10.5. This is the altitude of this right triangle. His book's the right angle of this right triangle, and that's an altitude. 10.5 is going to go in the geometric mean position. Between what and what?
Between x and 5.75.
Between x and 5.75, and it doesn't matter which order you write those two things. So I know that 5.75x will have to equal 10.5 times 10.5. Sometimes we might call that squared. So if I then divide by 5.75, what do you get for x? 24.92? The x is 19.17? Yes, no, anybody else? Yes? And then we do what, Ollie? If we want to know the height of it, we better add our 5.75, and then we get how much? 24.92 feet. So if I was guessing, I would probably guess that it was 25 feet tall. Maybe it's 24.92, but it's probably about 25. Okay, let's go to your book and let's do some problems from there together. Page, where are we? 541? Page 541, number 1. Number 1. It says find the geometric mean between each pair of numbers, and they give us 81 and 4. So our geometric mean formula we know is just the square root of 81 times 4. What is 81 times 4?
No, skip the examples.
I skipped the examples, and I'm doing your homework. We don't want to do that. Number 1, geometric mean between 5 and 20. I think somebody's awake in here. 5 times 20 is what number? 100. Square root of 100 is 10, so that was nice and easy, 10. Because after all, the ones the teacher does with you are always the easy ones, right?
Yeah.
36 and 4. So geometric mean is going to be the square root of 36 times 4, which is what number?
144.
And the square root of 144 is 12. 3. See, geometry is always easy. 40 and 15. Square root of 40 times 15. What is that?
600.
600?
Yeah.
And there's one that's not a perfect square. So let's go on. 100 goes into it. 100 times what?
6.
100 times 6. Square root of 100 times square root of 6. And the square root of 100 is? 10. Square root's of 6. Is that okay? Is 6 can be left?
Yeah.
Yes, there's no perfect square that goes into 6 evenly. So there you go. Even the teacher did one of those harder ones, and they're not hard. Number 4, write a similarity statement identifying the 3 similar triangles in this figure. So look at that figure there. I'm going to start out triangle CFD. Triangle CFD, and let's see if we can't figure out. So angle C, and CFD is the triangle on the right. Why don't we go ahead and go to that triangle on the left? What would angle C and the triangle on the right match up with? Angle E and the one on the left. So F and the one on the right would match with what on the left? F, because they're both the 90. And so EF, what's left? EFC. Similar to triangle, let's go to the big one. So let's start with that C in the little one. Matches with what in the big one? Let's just go on the far left triangle, the one we started with, the angle C matches with what angle in the big one? Which one? D. It matches with D in the big one. The little triangle on the left shares angle E with the big one. So the one it doesn't share must match with the D. And if I go back to the original, that F and the little one on the left, that F is the 90 degree. So what does it match in the big one? C in the big one. That's the 90 degree. DC, and what's our next letter? E. Number 5. Find X, Y, and Z. Let's start with X. Is X in a geometric mean position? Yes, it's an altitude. So we know an altitude. I'm going to put X in my geometric mean. It's a geometric mean between what and what? 3 and 12, those 2 segments of the hypotenuse. So X squared would equal 36, or X equals what? 6. Square root of 36 is 6. So that went nice and easily. Let's try Y. Is Y in a geometric means position?
Yeah.
Yes, it's a leg of the original, so I'm going to put Y in the means position of a proportion. Now, what is it a geometric mean with or between?
3 and 15.
Okay, 3 and 15, the segment next to it and the whole thing, or 15 and 3. And again, it doesn't matter. I'm going to write 15 and 3 just because that's the order that the theorem states it. The whole hypotenuse and the segment next to it. So this gives us y squared equals 45. Well, the square root of 45 is not an integer. What perfect square goes into it? 9, how many times? 9 times 3? 5. Square root of 9 times square root of 5. 9 times 5 is 45. And the square root of 9 is 3 square roots of 5. Z. Is Z in a means position?
Yes.
Yes, it's a leg of the original. So again, I can put Z in the mean spot, and it's a geometric mean between
Between
15 and 12. The whole hypotenuse 15, and 12 the segment next to it. So that gives us Z squared equals, what's 15 times 12? 180. We've seen this before. Square root of 180, what's the biggest perfect square? 36. 36 times what? 36 times 5, and the square root of 36 is 6. 6 square roots of 5. Number 6. Now it's the same figure. We've got a right triangle, and we drew an altitude there. So I'm going to start with that altitude. That's 16. That 16 is in a geometric means position. Let me write the 16 in the mean spot. What is it a geometric mean between? 8 and x. The altitude is a geometric mean between the segments of the hypotenuse, which are 8 and x. So if we did the cross products here, 8x equals whatever 16 squared is, and we can divide by 8, what do you get for x? 32? 32. So we were able to find x. Now as we looked at next one, let's go to y. Is y in a geometric mean position? Yeah, it is. It's a leg of the original, so I'm going to put it in the mean spot. And it's a geometric mean between what and what? Okay, that whole hypotenuse. Now we happen to know what x is. What's the whole hypotenuse? 8 plus 32, 40. 40, the whole hypotenuse, and what?
32.
And 32, the segment of the hypotenuse that's next to it. So this one gives us y squared equals, I don't know, what's 40 times 32?
It's 1,280.
How about the square root of 1,280?
It's
So how about a perfect square that goes into 1,280?
64.
64? How many times?
20.
20 times?
I don't know if that's 36.
So right away that tells me it's not the biggest. 256, does it go in? How many times? 5 times. Square root of 256 times square root of 5. What's the square root of 256?
16.
16 square roots of 5. Now don't give up hope if you did not think of 256. Maybe you thought of 64. You can still get there. We got there before. You just keep going until you have no more perfect squares. Z. Is Z in a geometric means position? Yes, it's an original leg. So I'm going to put Z in that mean spot. And it's between what and what?
8 and, or not 8. Yeah, 8 and 40.
Okay? I'm going to say the whole thing, 40, and the segment next to it, which is 8. 40 and 8. You could say 8 and 40. That's okay. Z squared equals, what's 40 times 8?
320.
320. And I bet that's not a perfect square root, is it?
No.
So what is a perfect square that goes into that? 64 times what?
5.
64 times 5? Square root of 64 times square root of 5. What's the square root of 64?
8.
8. 8 square roots of 5. Number 7. Corey is visiting the Jefferson Memorial with his family. He wants to estimate the height of the statue of Thomas Jefferson. Corey stands so that his line of vision to the top and base of the statue form a right angle, just like we saw earlier. As shown in the diagram about how tall is the statue. We'll notice again that altitude that's going straight across from his eye, that's a geometric mean. And how long is that?
8.
8 feet 8 inches. Well, let's put a geometric mean position. 8 feet, now we need to keep it in the same unit. We can't mix feet and inches. 8 inches out of how many inches in a foot? 12. 8 out of 12. What does that reduce to? Not a decimal, but what does that reduce to? 2 over 3. 8 and 2/3. 8 and 2/3. 8 and 2/3. That way we're going to get an exact value out of this thing, hopefully. So that's the altitude. It's a geometric mean between the segments of that hypotenuse, which are running up and down Thomas Jefferson. What's the bottom segment? 5 feet 8 inches. So that would be 5 and 2/3 again. And then the top part, x. We don't know the top part of that hypotenuse. I'm actually going to turn these into improper fractions. Or you can go to your calculator, but we like to use our brain. 3 times 8 is 24, plus 2 is 26/3. So I have 26/3 times 26/3, or I have 26/3 that is squared. 5 and 2/3, 3 times 5 is 15, plus 2 is 17. I have 17/3 times x. And then if I want to know x, I multiply by 3/17. You guys working on it yet? That probably didn't help you. You have a fraction answer yet? Or I'll tell you. It's that, whatever that is. What do you get? Anybody else? Is that what you're getting? 676 out of 51? Let's divide it out. How many times does 51 go into 676? Just take 676 divided by 51 and tell me the integer. 13? It's 13 point something? So it's 13 and then go 51 times 13. So we'll know how many whole times it goes in. 663? So 663 and the 676 is 13. 13 out of 51. Wow. Feet. I would take a decimal on that one, Josh.
That's what I was about to ask.
I figured that was your question. I would take a decimal on that one. Your assignment.
We just learned to feed into it.
Oh, that's not done. Whole statute. That's not the whole statute. What do we need to do to get the whole statute?
Divide the 2/3, add 5.
We need to add 5 2/3 to that to get the whole statute. Plus 5 2/3. We're going to go to a decimal at this point.
Yeah.
What are you getting?
I got 18.9.
18 point what? 18 point what? 0.92? So about 18.9? 18.9 feet. That works. 18.9 feet is the height of the statue. All right, your assignment at page 541. Numbers 1 through 14, of which we have done the first 7 together. 19 through 32. 36 through 38. Still almost a half hour in class to work on that.